here, and I'm looking for this path here. Everybody see that? Times 5% plus what are the percentage of the type 2s? 60%. And the conditional probability that it has a Blu-ray player if it's a type 2 is 80%. So if you calculate that out, what do you get? So what, we got 0.4 times 0.25 plus 0.6 times 0.8. So I get 0.58. i.e. there's a 50% chance that a sold model 58 has a Blu-ray. So that would be the typical question you would have to answer with conditional probability. Okay. Another, this is using the decision tree. Another, has everybody got this? Everybody good with this? All right. So here's another one. So consider the roll of 2 fair dice. Just my kitty is here trying to get my attention. What, Tommy? What do you want, little boy? Here's another type of conditional probability. So you're going to roll 2 fair dice. Okay. So you would ask, what is the probability that let's see, what is the probability that you rolled a 10, assuming that you rolled doubles? All right. So what is the probability that you rolled a 10, assuming that you rolled doubles? All right. So let's look at these 2 events. So what's the event for rolling doubles? We'll call E1 is for doubles. Okay. Well, that means you rolled a 1-1, a 2-2, a 3-3, a 4-4, a 5-5, or a 6-6. Okay, and E2 is going to be that you rolled a 10. What are those probabilities? Well, what are those possible rolls? You have 4-6, 5-5, 4-6. Okay, so if I ask, what is the probability that E2 occurred, assuming I know that I rolled doubles? Okay. So I know there's only 1 in common in the intersection, right? So this is going to be the probability, okay, just using the formula of the intersection over the probability of the event that I knew. Everybody with me there? So I'm thinking it should be something like 1/6, right? Because of these 6 so I know I rolled doubles, and this is the one I want. But let's see. Okay, what's the probability that they both occurred? Well, they only have 1 in common, so that's what, 1/36? And what's the probability that this one occurred? Well, that's 6/36. And as expected, we get 1/6. Okay. You can view this as, so notice in these cases, notice this denominator is also always going to cancel out. Okay. So you're really just looking for, given that this is, it's like you're saying this is your new sample space. Okay. I knew that it had to be one of these. Okay. Given that, what's the probability it's the one I wanted? Does everybody see that? Okay, so those are the two types of ways that you're going to use conditional probability. Yeah, that other problem where you have the changing probabilities, that's not something I would ask on the exam, and I doubt she's going to ask that. But definitely one of these other two types of conditional probability problems, absolutely. Any questions about that? Can everybody see what's going on there with the conditional probability? All right. Okay, any other questions? So if there are any others, we'll just go back. We'll start looking at some exam review. Anything else? Yeah. Bottom line, if it wasn't in the Rosen book, it will not be on the exam. And I'll be the gatekeeper for that. If she asks something or pulls a problem out of the Epps book that just wasn't covered in Rosen, I'll flag it. All right, so should we go back to where we were with just some general exam review? Does anybody else have any more homework questions? All right. All right, if you do, just pipe in. All right. So last time we sort of reviewed up through functions. So the next thing we had on our plate was sequences. Right. And we had two particular type of sequences that we looked at. We looked at the arithmetic, which was of the form, so you had some starting value and you added some multiple of something for every new value. So for example, something like, I don't know, 3 plus n times, no, let's not make it 2, let's make it about 4. Oops. So if these are by terms of the sequence, what would the sequence look like? What would look like 3, then 7, then 11, then 15. So this is like my A0 value, and then all of these, what do I do? I add the 4 to get to the next value. So if I were going to do this in recursive form, remember the recursive form of this was the kth element is the k minus 1 element plus 4. Okay, so this was the recursive form. Okay. And this was the roster form. Okay. And this was the closed form.
For recursive, do you have to specify the A of 0 term?
Yeah, and you got to say the A0 is 3. You got to make sure you get you're right. You need the initial condition.
All right, thank you.
Okay, so we had these 3 forms. We had the recursive form, or the recurrence relation with the initial condition stated. You had the roster form, and you had the closed form. And so we had problems where you had to try, given some sequence, either in roster form or recursive form, you had to try, you had to find the closed form. And the way we typically did that is, well, we basically writing out the elements and see if we can see the pattern. And we had several examples for doing something like that. And then we had the arithmetic, then we had the geometric. Okay. And this was, you had like a to the n equals, I don't know, some constant, we'll call it c, times some rate to the n. So something like maybe this is something like a to the n equals 3 times 2 to the n, something like that. So this was the closed form. So what would the recursive form look like? It looks something like 3, then times 2 is 6, times 2 again is 12, times 2 again is 24, times 2 again is 48, and so on. Or what was the recursive form? We take the previous value and we multiply it by whatever the rate is. So 2. Okay. And then, so the initial condition, A0 equals 3, gives our starting point. All right. Were there any questions on those? Any questions on sequences and going back and forth between the recursive and the closed and the, I mean, I wouldn't ask anything more complicated than this stuff. All right, then we had series. A series, which are just summations. All right. So something like, I don't know, k equals 1 to 5, 3k plus 2. All right, so ways we did this is, okay, you could do it in roster form. You could calculate each, if as long as there aren't that many, you could just calculate them out. So what would this be? 3 times 1 plus 2, so that's 5. Plus 6 plus 2 is 8. Plus 9 plus 2 is 11. 4 plus 2 is 14. 17. Okay. All right, so if you add all those together, whoops, plus, comma. So you add those all up, what do you get? 31, 42, 55. All right, so that was one way to do it. The way that you should, because these numbers might be large, is we use our linearity principles. So we break this up into or 2 times. That's the way we're used to. All right, but then to calculate these individual parts, and we had a bunch of equations. This is our Gauss. we had for k squared was it n, 2n plus 1, n plus 1 over 6. And for k cubed, okay. All right, so we had problems like this. So the key, anytime you see anything like this on an exam, it's asking you to make sure you know about this linearity principle, that you can distribute this, in a sense, distribute this summation to the different terms. Okay. So this is a typical type problem. This is a type of problem. Well, I did put a problem like this on our exam, on one of our past exams. Okay. And then we had this notion of telescoping sums. Can somebody mute? Who's doing? Oh, Sam. Can you mute, please?
Oh, sorry.
Yeah. All right. Okay, where if I have, like, say, a to the k minus a k minus 1. So if I have these terms where this, we'll write this out. So this is like a1 minus a2, or excuse me. Let's do it like this. Okay, so this is going to be something like a2 minus a1 plus a3 minus a2. If we keep going, we're eventually going to get to ak plus 1 minus ak, or n plus 1. And then we have the situation where we have all this cancellation throughout. So the only thing that ends up being left is this term and this term. Okay, so we know that this is all equal to a to the n, oops, plus 1 minus a1. Okay, so we use this as a technique to very quickly calculate stuff like this. And then we had our geometric series. Is it just right some? That's okay. Is a general right k equals 0 to n, or have it written as sum k equals 1 to 1. It's really sort of up to you. Really sort of up to you. Whatever the problem calls for. But so what did we have? We had that when I have the sum, if I have a finite sum, k equals 0 to n of sum a times r to the n. So remember, what was this? This was r to the n plus 1 minus 1 over r minus 1. Hopefully I got that right. And as n went to infinity, as long as the absolute value of r is less than 1, then we had the special form that this equaled 1 over 1 minus r. Okay, so just know how to use these two different formulas. And be careful of limits. These start from 0. So if they don't start from 0, you've got to adjust on the back end here. All right, we had problems that. Any questions about those kind of problems? Just applying these formulas. That on an exam, it shouldn't be anything harder than applying one of these formulas. Okay, 2.5 is not going to be on the exam. So the only thing in chapter 4 that she put down to be on the exam was this first section, 4.1. So she's not even going to ask you about Euclid's algorithm. Okay. So the only things that you really need to know from chapter 4 is know the definition of divides. To say that n divides m means there exists some k such that m equals kn. Okay, that's the definition of division. Okay, it is not anything like this. Okay, if you start to write anything something over something when you're working in this in these integers, stop yourself. Okay, that's not our definition. Okay, remember this definition is problematic because it doesn't allow n to be 0, but 0 can divide 0 because, I don't know, 0 equals 1 times 0. Okay, so we don't use this definition. Okay. All right, so what are the things from this chapter we needed to know? Well, so we had our theorems. So we had if A divides B and A divides C, then A divides B plus C. So, if 3 divides, 12 and 3 divides, 15, then this means that 3 should divide 27. Okay. And if A divides B, then I can go ahead and multiply B by anything. A will still divide the product. And I had the transitivity. If A divides B and B divides C, that applies that A divides C. And if you put these all together, we had if A divides B and where is it? Yeah, A divides B and A divides C. Well, then I can put all these together. I know that A divides any multiple of B plus any multiple of C. Now, one of the most important parts of this course is the division algorithm. So you need to be, yeah, I'm sorry, you got a question? Was there a question? Okay. So what does the division algorithm say? It means that any number n, any integer n, can be written uniquely as some quotient times some integer d plus some remainder r. And this is unique as long as this remainder is between 0 and d. So if I constrain this remainder between 0 and d, then this is unique. So this is just a statement of doing something like this. D into n, okay? You're going to get some quotient, and after you do division down here, you're going to get some remainder. I mean, this is the application of this to actually doing division of integers, but this is where it comes from. Okay. So, all right. So, given a number, given two numbers, you need to be able to put one. You need to be able to put one of the numbers in this form using the other number as the divisor. So, if I gave you, for example, all right. So, for example, let's say I gave you the number, I don't know, 1, 2, 3, 4. Okay. And give you the number, how about 97? Okay. And I want to write this in the form 12234 equals 97 times some quotient plus some remainder. Remember, this remainder has to be from, this remainder here has to be from 0 to 96. So what was the procedure for doing that when I'm dealing with all positive numbers here? Okay. So start by dividing. Just on your calculator, just divide. And what do I get? I get 12 and something. It's like it's about equal to 12.7 something. Okay. All right. So it's a positive number. I want to take the floor of that. Okay. Which gives me 12. So I know that 97 at least goes into this 12 times. Okay. So I know that this Q is going to be 12. That's my Q. So how do I find the remainder? It's 1234 minus 97 times 12. And what does that equal? 70. So 1234 equals 97 times 12 plus 70. So that's the division algorithm form of that number. Any questions about that? So notice in this example, when I've got a positive number, I try and get as close as I can, and then I'm going to add some more to it, right? That's what's happening. That's what this procedure is doing. So any questions on this procedure when this is a positive number? Okay. Now, how about with this is a negative number? Let's do negative 1234. What was the other? What was my D? 97? Okay. Right now, what's going to happen? Well, remember, my R is always positive. So what's going to happen here? Here's 0. Here's my N. It's negative. So my R, I'm always going to go in this direction. So I'm going to have to look to the first number that ends up over here, so that I can then add the positive R. So I'm going to go a little past. So once again, let's divide this. So what this was negative, what was it, 12.7? Yeah, negative 12.7. Okay. So now when I take this floor function, okay, so it's the greatest integer less than this. Well, so I was at negative 12.7, so notice I have to go backwards to 13. Because I need to go to the left. I want the next integer to the left. Okay. So now what's my remainder? So minus 1, 2, 3, 4. And then what is this? This is minus 13 times 97. What does this equal? Like 26.
Oh,
Okay, so notice in this case, negative 1, 2, 3, 4 equals 97 times negative 13 plus 26. So the answers are a little bit different because in this case, I had to go past to the left. So any questions about how to, given a number, find its division algorithm representation?
I got a 27 for the remainder.
Did you get 27? Did I do it wrong?
I got 27.
Oh, yeah. I typed in something. I typed in the wrong number.
Oh, okay. Thank you.
Yeah.
I just want to make sure.
27, yeah. You're right. All right. So, I mean, this would be a typical problem. Break something down into its division algorithm form. All right. So then the other thing in 6.1 was doing this modular arithmetic. Okay. So remember, so this expression, remember what this expression, well, let's do them both. Let's do both the expressions. So we had two expressions that came out of this division algorithm. So let me write the division algorithm. All right, so we had two expressions out of here. Okay, so n div m wanted this quotient value, and mod m wanted the remainder. So these were two expressions to pull out these values from the division algorithm form of n. Okay. So this one we don't use so much, but this one's important. This one we use a lot. Okay. And so, let's see, did they do the, I don't think, did they do modular congruence in this? I don't think they even did modular congruence in this section. Did they?
No, it goes straight from division rule to tree diagrams in the book.
Yeah, where did they do congruence? Where was modular congruence? Oh no, here it is, down at 254, right? Okay, so we had this notion of modular congruence. Right, and we had some definitions here. So in order for A to be congruent to B mod M, right? So this is the syntax we use to say that these two are equivalent. Mod N means that these two remainders are the same. Okay, so if I took and I did division algorithm expansions of A and B using N as the divisor, I would find out that those two remainders are the same. And this was, remember, this is equivalent to the other definition that N divides A minus B. Okay, so we had these two working definitions. I started with this one because I think since it harkens right back to the division algorithm, and then I proved this one, but your book starts with this one and proves this one. Just be aware of both definitions. Okay, so in order to, so typical problem might be, so R 121 and I don't know 56 equivalent mod 7. Okay, So yes, you could use the division algorithm and find what the two remainders are here, but simpler is just to use the second definition. So you subtract them, and what do you get? So that's 65. But 7 does not divide 65. So the answer is no, they're not equivalent. But if I did instead 119 and 56, okay, so what's 119 minus 56? That's 63, right? And 7 does divide 63. So 119 is equivalent to 56 mod 7. Okay. So given two values and asks if they're congruent mod n, you should just go ahead and use this definition here. Just see if n divides their difference. Any question about that? All right, so then let's see what was next. Oh, there were a couple theorems that said that we had a theorem that said that if A and B are modularly congruent mod n, then every B, so every A can be written as B plus some integer multiple of the mod. And we use this to build up these sets of modulo equivalent things. So for example, what if I started with A equals, I don't know, 4 and B equals, and N equals 3. I wanted to make the set of everything that's modularly equivalent to 4 mod 3. So I can just start adding multiples of 3 in one direction. So 3, 7, 10, 13. These are all congruent modulo 3. And then I subtract going the other direction. 1, -2, -5, and so on. So all these values are congruent modulo 3 by using this theorem. All right. Any questions about that? Building these sets. So if I gave you, if you had a question where you were given a base value and some modulo and some remainder value, you should be able to build one of these sets using this theorem. Right, then we had modulo arithmetic. Well, not quite modulo arithmetic yet. We had theorems that said that, so here was a theorem. We said that if A was equivalent to B mod n, and C was equivalent to D mod n, okay, then we had some relationships. So if we add A and C, that'll be equivalent to if we had added B and D mod n. And we had a multiplication rule as well. Okay. Oh, what's the typical problem for something like this? Now, let's see. What kind of problems did they show us in the examples? Well, nothing all that, nothing all that earth shattering. They just had the example they gave is just a direct representation of the theorem. So what did they tell us? So they notice that 7 is congruent to 2 mod 5, and 11 is congruent to 1 mod 5. So 7 plus 1 should be congruent to 2 plus 5. Oh, 2 plus, I'm sorry. 7 plus 11 should be equivalent to 2 plus 1. Mod 5. So they're saying that 18 should be equivalent to 3 mod 5. And that should be true because 3 mod 5 is just 3. Yeah, what's the expansion here? 3 equals 0 times 5 plus 3. So notice anything less than your remainder value, be modded, it's just going to be that value. And 18, what is 5 times 3 plus 3? So again, mod 3, mod 3. Mod 3. All right, so problems like that, those aren't very interesting. The more interesting ones look like this. Okay, so we have a theorem. That said that if we add two values and then look at the remainder, what I could have done is I could have taken the mod of each thing individually first, i.e. reduce these values. Okay. And likewise, if I had multiplied the two values, I could have just multiplied their mods. Okay. So it gives you a way to, if you're trying to find out the remainder of something large, you can break it down. So for example, if I wanted to do, 100 mod n, how about mod 3? Okay, I could break this down maybe into 50 plus 75. 275. Yeah. Okay. So now I could take each of these individually. Well, 73 divides 75, right? That's what, 15? I'm sorry. 25, right? So this is just 0, right? So I ended up with just 50 mod 3.
Wait, what? Why does it become 50 plus 75?
Oh, 50. I'm
100?
sorry. I meant 25. I wrote the wrong thing.
Oh, okay. Okay, thank you.
25. Okay. So this whole thing just comes down to 25 mod 3. And so we know that's just 1. Because 3 times 8 is 24, then there's 1 left. Okay. So if this is really big, sometimes I can break it down like this and come to a quicker answer. And this is really the case when you have multiplication. So what if I had instead said 100 mod 3? Okay, so that's the same as 10 mod 3 times 10 mod 3. All right, well, I know that these are just 1, right? 10 mod 3 is just 1 because 3 times 3 is 9 plus 1. So this is just 1 times 1 just equals 1. Okay. And we did examples where, this was really big, like 100, maybe to the, I don't know, how about to the 20th, something like that. Okay. And so we broke this down using our exponent rules into easier chunks, and we reduced it down and down and down. So for example, so there was sort of a corollary here that he didn't really give, but if you wanted to do something like a to the b mod n, what you could do is do a mod n to the b. Okay. And break this down continually. And we did an example like that. So just to reference your notes on that example. I don't think she's going to ask anything like this. I think it'll be more something like this. Just know how to use the sum and addition formula to break down what you're doing so that you have something easier to figure out. And the last thing in this section was using this principle to do modular arithmetic. So we defined our plus operator. We put this little m underneath it. So what this is saying, what I really want is I want you to add a and b and then figure out what the remainder is mod n. And in order to do that, so if I want to add two things and get the remainder, well, then I can just use those previous theorems. I can break down a and b, and likewise, so once again, I use the theorems to break down a and b to find out what it is mod n.
You have to complete it by 4:15.
I'm sorry, what's our question? All right, so any questions about that modular stuff? She's only asking for 4.1, so she's not going to ask about integer representation. She's not going to ask about Euclid, which is a pity because Euclid makes for nice exam problems. So nothing about primes, nothing about Euclid. Okay. Then we get into the more recent stuff that we did. So proof by induction. So make sure that you can break a proof down into the base case, the inductive hypothesis, and the inductive step. Was 5. I guess 5.2 was on that list. So we had normal induction and strong induction. Where here you just assume in your inductive hypothesis, you assume for some k. Here you assume for everything from 1 to k. That was the difference between the strong and weak. That's fairly recent, so I won't go into a bunch of that. I know you've got examples. So just know how to do a proof by induction. If I were going to ask a question on the exam, I would ask something like I did on the homework. Um, and let's see, what do we have next? All right, then 6 was all of our counting stuff, our binomial and our pigeonhole, which we just did, so I won't really talk about that. And then 7 was applying our combinatorics to probability, which we've already talked about. I mean, so that's a pretty good rundown of everything that you need to know. Let me check my email real quick, see if she sent me the exam. I might as well check that right now while I'm got y'all. Let's see what she says. Right. Okay. So I don't know. She still hasn't sent the exam. So I apologize for that. I wish there was something I could do about that. All right. So, I mean, that's really about it for the exam review. Did anybody have any other questions?
Professor,
Yeah.
for the exam, is it going to be the same layout as the homework has been with like the multiple choice and fill in?
Yes, because those are the types of questions that WebAssign has. So yes, that's going to be the format. That's why I assigned a bunch of homeworks on WebAssign to get you used to it.
Okay, thank you.
Professor.
Yes.
So, my trial gonna end like today. So, like, do we ask them to extend it again or something like that?
There's supposed to be a button that pops out that says extend free trial.
Okay.
A lot of people are having problems. So what you can do, and in fact, if you see that your trial is going to expire like a day or two before the exam, call them now. Get in touch with the customer support now and ask them to extend it. Now, what students have been telling me, apparently their customer service isn't fully briefed on the situation, but there is a case number. Does everybody see the case number that I posted in Canvas? Yeah. So if you call them, give them that case number and say, hey, a lot of people are having trouble getting their thing renewed. The exam is on the 16th. Will you please just renew me now? Here's the case number for this situation, and just have them do it. Now, what I've been told by students is that what they're actually doing is they're just giving people a license and not really even just extending the free trial. They're just giving people a license. So if they do that, fine. It's just whatever the heck works. Okay.
All right.
Oh, Lena's here. Oh, I'm sorry. Go ahead.
Oh, and for each problem we have like 1 or 2 try, right? Is that?
I think it's going to be 2 tries. So if you goof up, if you accidentally, enter something wrong, you can correct it. But I think that was the final. I will let you know if that's different.
All right.
I believe it's going to be 2 tries.
Thank you.
All right. Aline, I know you had homework questions. I see you've joined us. Do you have a homework question? Oh, finally, I scheduled in at 11:15, Cal. So 9 o'clock to 11:15. Aline, do you have a question?
Would it be anything on the exam similar to the number 4 from exam 2?
Number 4 from exam 2. Let me double check on what 4 from exam 2 was. Let me get my book here.
Okay.
Where's my folder?
It was the drawing one where it asked to show.
Oh, the drawing one.
Mm-hmm.
Oh, that's right. Right. Yeah. So, probably not, because you're not going to draw in. You're not going to draw in WebAssign, but you should understand. For example, if they gave you something like this. Let's see. Okay. they had a little fill-in box here and an S here. You might have to determine, what goes in this little box. Okay. And so in order to figure that out, you might want to actually do a diagram. Okay. So you might on the side, in order to answer the question correctly, okay, if this is S here, you might actually want to draw this little diagram and say, okay, well, here's F of S. Okay. And ask yourself, if I go back, if I then take the pre-image of this, do I just get what's in S? And you would look at that and go, oh, no, wait a second. You know what? There could be something out here going into here. So there might be things in this pre-image that weren't in the original set. So you would have to know that you have to say that this is actually a superset. S is certainly in it, but it's a superset of S. So you might need to do a diagram like this to answer the question. So what was ours on our exam? We had, oops. Oh, it looks like do they limit you to 20 drawings or something? Oh, I see. I think you clear everything forward. Okay. Yeah, so what was our exam? We had this, right? And they might want you to do a fill-in to say, okay, what's this relationship to T? So once again, you might want to do a diagram just to, here's T. So you know that there's going to be some pre-image here. There's the pre-image of T, and you want to know, okay, what happens if you then go forward from this pre-image? What happens? Well, then you should be aware, like in the exam, that here's the thing that's actually mapped. So this is the only thing you're going to get back. So you should know that this is actually just a subset of. Okay, so you might have to draw one of these diagrams so that you can answer the question as an aid to you, to see how to answer the question. But you're not going to be drawing these, and entering them in WebAssign, as far as I know. I don't think WebAssign has a way to do that even. Right? Lee, didn't you have a question on problem number 2 on the first exam or something like that?
Yeah, it was the Knight and Knave one.
Yeah. Okay. There's no. I didn't see Knight or Knave in EPS. Did EPS have Knight or Knave in it?
Not that I saw.
Yeah, not that I saw. So I wouldn't. Yeah, I don't. Since it's not in EPS, there's not a WebAssign problem for it.
Okay.
So
Thank you.
I see. I wouldn't worry about that.
Could we possibly go over number 9 from the first exam? I believe it was a proof by contradiction.
Yeah. What was it?
For all n and m that are integers, n times n is even. If n times m is even, then n is even or m is even.
All right. Okay. So say it again slowly. Let me write it down. So for all m and n
that are integers, n times m is even. If n times m is even, then n is even or m is even.
Okay. All right. And how did I ask you to do this?
It just says prove, but I believe it's a proof by contradiction.
Well,
it may be a contrapositive.
I did contrapositive.
Yeah, I think it's a contrapositive.
This is more for a contrapositive. So what's the
Yeah.
contrapositive of this?
Should be n is odd or m is odd. Then
Not
n
or, not or.
and m is odd. Oh, that's there we
That's
go.
number 8.
Which
'Cause we-
that one I was able to prove.
So the contrapositive would be number 9.
Oh, right.
So
I mean, not number 8. Yeah.
So, all right.
kinda
So that
just-
right. So you prove this in number 8. Then
yeah.
I asked you to prove this, and the idea was for you to say, "Oh wait, that's just the contrapositive of this."
Oh, okay. Oh,
Done.
okay. Thank you.
Done. No more. Done. Finished.
Yeah.
That's all you had to do.
I got 8. 8's no problem. Then yeah, perfect. Thank you.
All right.
Professor, are there any questions on infinite sets?
No, 2.5 will not be on the exam.
Thank you.
Like just those sections that I listed in the announcement on Canvas. Okay. So, Aline, did you have any more? Was there any more homework problems, or it was just number 4? That was it.
Yeah, I'm good. Thank you.
All right. Anybody else have anything else?
Could we go over a proof by induction problem? From
Sure.
one of the
Do you
homeworks?
do you have one in particular you'd like to do?
Yeah, it is. It's for every integer n that's greater than or equal to 0. It's the summation from I equals 1 to n plus 1 of I times 2 to the I equals n times 2 to the n plus 2.
N times
2 to the n plus 2. And that plus 2. That thing plus 2. And that's the total.
Okay, do I have it right?
Yeah.
Okay. So, step 1, we say proof by induction on n. Okay, so it makes it clear what our parameter is there. Okay, so what did you choose for a base case?
I believe it's 0.
Yeah, because I want from n greater than or equal to 0, so choose n equals 0. Okay, so this side becomes I equal 1 to 1 of I to the I equals 1 times 2 to the 1 equals 2, right?
I think it's 2 to the. It would be 2. Oh yeah,
Okay.
2 to the 2, because we have 0 plus 2, and the 1 times 2 to the 1 would be 2 to the 2. Oh, I mean to the
Oh, did
3.
this start from 0 or 1?
It starts from 1. I'm just the n times 2 to the n plus 2. You have 1 times 2 to the 1.
Oh, yeah,
Wouldn't it be?
yeah. This side over here. Oh, to n plus 1. I'm sorry. It's n plus. So we're going from 1. Oh, no, we're going from 1 to 1, 0. So this is, yeah. So over this side, remember, so
Oh, I'm sorry. I was confused. I didn't realize you put it was I times 2 to the I is what you were writing in.
yeah. I'm sorry. Did I confuse? Yeah.
No, I just didn't see it.
All right. So this side over here, this is 0 times 2 to the 0 plus 2 plus 2. So this thing's just 0. So this equals 2. Okay.
Oh, okay.
So the base case works.
Yeah.
Okay. So we're going to assume that this is true. For n. Okay. So now we're going to consider n plus 1. Okay, so let's see, what is it that we want to see? Okay, we want to see that I equals 1. So if I put n plus 1 in here, I get n plus 2. So I want to see, so if I put n plus 1 in here, I should get n plus 1. Is this plus 2? Yeah. So this is n plus 3. So this is what I want to see. That's what I want to come out. Okay.
Okay.
Okay, so let's look at this. So I've got I equals 1 to now n plus 2 of I to the I. Okay, so anytime we see something like this, we want to get back to something like this. What's the technique? Well, I pull out, I start to pull out things. Okay? So if I want this back down to this, so what did I pull out?
1.
Now I pulled out the n plus 2 term, right?
Oh, okay.
All right. So what I have left, I have n plus 2 times 2 to the n plus 2. You see that?
Yeah.
Okay. So now, according to the inductive assumption, what does this equal?
The first, the initial one, and to 2 n plus.
Yeah. Okay. And see, then what do I have? Okay, so if I do some algebra now, so I've got n to the 2n plus 2, and I've got n plus 2 to the 2n plus 2. So if I put those together, what do I have? How many 2 to the n plus 2s do I have?
N times n plus 2? Or, I know.
Factor this out. If I factor this out, what do I have left? I have
n plus 2 plus n, I believe.
Yeah, which is just 2n plus 2.
2n plus 2, yeah.
Okay. And I'm almost there. How can I get from here to here now?
You would set them equal.
Well, no, but I want to get to here, but I'm not quite there. I look like this. I want to look like this.
I'll factor out the 2.
Yeah, factor out a 2.
2.
Okay. What's the final step? Here's 2 to the n plus 2, and I'm multiplying by another 2, so what do I have?
Factor out another 2, I believe. Or, you just put it in there.
Yeah.
That's what I forgot. Like trying to get the n plus 3.
There you go. There you are.
Oh, okay. Okay, thank you.
Mm-hmm. The algebra is a little trickier on this one, but this is with if you see proof by induction and summation, you know you're going to be taking the n plus 1 terms out of the sum.
Oh, okay.
You know that's what you're going to do.
Oh, okay, thank you.
Mm-hmm. Everybody good with that? It's a little harder to do things neatly on this whiteboard.
Oh, yeah.
I'm used to writing a certain size on the big whiteboard. Are there any other questions? Let's do a quick double check, see if in the last couple of minutes if she sent the exam, and I do not see it.